These notes are going to be about multiplying infinite series, integrating and differentiating term by term, and the Lagrange error bound. The warm-up today is just some review over the series test for convergence or divergence. This is conditionally convergent, and this one's absolutely, these are both divergent by the nth term test, and then this is the only one that is conditionally convergent. It originally is divergent compared to 5 over k, or 1 over k, whatever you would like to put, but then that's for the absolute convergence test right here, and then we focus on this, which would be the alternating series test. So it is conditional because it is alternating. And then this one is a Maclaurin series. The Maclaurin series, all you have to do is really substitute in a 2x instead of an x. And I did put one up here for the derivative, but just work through it. And when we take the derivative, just like a normal, we keep n as a constant. So this doesn't change. But we have two different ways to do it. You can do this really long way, or you can do this shorter way, which is you have this function, take the derivative of it, and then use that to find what it is spread out. And this should be, my bad, 2x to the n power. All right, same exact thing. This one's probably easier to understand. So whichever way, you can look through that. So our notes today, not too crazy, a little bit more algebra based. So the AP exam requires that you're able to recognize a function by the terms of its infinite series. So for the examples below, write an infinite series for e to the x. We should know that that one's a memorized. Just like we did for the warm-up, e to the 3x. We're going to replace that x with a 3x because the x changes to a 3x here. Write the first 4 series. Again, we start at n equals 1, or 0, sorry, which is 1, and then we keep going, which is the first 4 terms, right? So this is the first, second, third, and fourth term. So you kind of got to think about it like that. They're two different things. Starting at n equals 0 is the first term. Then we have, compared to this, we have the sum of the series here. The only thing that's really different between these two is instead of a 3x, there's just a singular 2. So it's going to be looking like this, but instead of an x, there is a 2. So that therefore it's going to be e squared. Multiplying infinite series basically is just distribution. Because remember, this summation is only really dealing with the n's, equals 0, or n equals 1, whatever it is. So the x squared can just kind of stay up front. It's kind of, we treat it as a function, and then this is dealing with those n's to be constants or numbers, whatever. So the x squared, and then I listed out what this is starting at n equals 0 and kept going, and then I just distributed. So I multiplied everything on the inside by x squared and got this answer here. When we multiply 2 infinite series, it's pretty crazy. You don't have to go this far out, right? That's a lot, but it does help you to make sure you don't miss anything. Like the ones, there's nothing else. 2x, there's 1 here, 1 here, so those match. And then we have to keep looking past. Usually we can look to the second or the third power depending on what they're asking. If they're asking us to go to the 4th term or the 3rd term, this is just basically algebra. So example 1, find the first 3 non-zero terms of the Maclaurin series for f of x equals e to the x sine of x. So I'm going to do the Maclaurin series for those ones, which is xn over n factorial times the sine So I'm just multiplying this, right? So e to the x and then sine of x. So I'm just coloring this in. Right, just multiplying that. because they're Maclaurin series, so we know the memorized of the version. So for this one, we can just start listing out the terms. Dot, dot, dot. And then we have x minus x cubed over 3 factorial. And you don't have to memorize this. Obviously, you can just start plugging in n equals 0, n equals 1, n equals 2. If you are lost with how to do those, just start listing out the terms using the summation. Again, and then we're just gonna multiply. You don't have to go as far as I might go. X minus x cubed. Right, so I'm just doing my foiling forever. And go to the next term, x squared over 2. Oh, I forgot the fourth one. My bad. And I can just stop there. You can keep going. I did in my notes, I did keep going a little bit, but I'm only looking for the first 3 non-zero terms. And I see this one, and this one are gonna be used. So I'm going to add those up together. So x minus or plus x squared. Where's my other? I'm missing an x squared. Oh goodness. What did I do? Oh, I don't know why I did that. That should not be over 2 factorial. My bad, that's why. And then, so those match. All right, this. Then we have negative 1 over 6, technically, and then 1 over 2. So we're going to combine those. We'll get x3 over 3, and that's just forever and ever. But we only wanted to find the first 3 non-zero terms. So you could keep going forever, but we only needed 1, 2, 3 terms. And again, I just found a common denominator for this one and this one. So just a simple multiplication, foiling. The second one, we're gonna integrate these series. So there's 2 options to do. Choose whichever one makes the most sense for you and that you'll remember how to do. You're gonna integrate the general term. The general term for this one is just integrating what the summation form looks like. And so I use the e to the x Maclaurin series. How do I know it's Maclaurin series? Because it doesn't tell me it revolves around anything else. So if it revolved around, like, let's say a equals 1, then I'd have to do a Taylor series, but it's just the Maclaurin series for this one. And so instead of the x, I put a negative x squared. So that's how I got that. And now what I'm going to do is I am going to take the integral of that. Oh, I got to get my dx there because we're integrating with respect to x. So make sure you don't integrate with respect to n because n is technically our constant. I'm going to separate this out a little bit, make it a little bit easier for me. So we have the negative x squared. That's a negative 1, right? Just pull out the negative 1 to the n power. And then we have x to the 2n dx. And then we're going to kind of leave this part alone a little bit. Why? Because these are technically a constant. Right? Think of it, if this was 1/2 or negative 1/2, whatever it is, we'd pull it out front of our integral in the first place. So that's why we're really not going to deal with it. We're just kind of pull it out front, just like a normal constant. And then we're going to deal with just the x because, again, we're integrating with respect to x. So summation. I'm going to just leave the first part. And then we're going to treat this just like a normal integration, x to the 2n plus 1. Remember, n is a constant, right? It could be 2, it could be 3, whatever it is, divided by 2n plus 1. And then we do our plus c because we have no limits of integration to compare it with. So that's one way to do it. The next way is to integrate it term by term. So I'm going to keep the same thing. I'm going to just copy this from up here. And I'm going to start writing out the terms. So I'm going to integrate, and I'm going to start at n equals 0 to 0 is 1, x squared over 2 factorial. And you can keep going. But I'm just going to integrate it. X. Keep going from there. And then we're going to find the things. We're going to make a summation from this. And I know it's going to match the top one, but I'm making it seem like I've never done this one before. So we can check it the other way too. So I know it's an alternating, right? It's going minus plus minus. So do the alternating. Then when you're starting at 0 and then go to 3, 5, and we know that one looks really familiar to our sign. We have n factorial, and then we have 3, 5, and 7, which means we have 2n plus 1 to make those odd numbers. And then we're also adding our plus c variable because they did not give us an initial term. And if we zoom out a little bit, these should match exactly. It's a good way to check, do them both ways. So either way works. Okay, example 3, we have find an infinite series for the integral from 0 to x sine of t squared dt. Start out by writing. And I'm going to put this into our Maclaurin series, but I'm going to replace the x where it normally is with a t squared. And again, we could do it a couple different ways. I'm gonna choose for this one to pull it out and integrate it by term. Mostly because I can just do it pretty quick. And it's a little bit easier for the integration. Again, you can do it either way that you want, does not matter. Just make sure if you do it one way, you check your answer, hopefully the other way. dt. Okay, then we're just gonna integrate it just like we normally would. Oh, with respect to x, my bad. X. Oh wait, no plus c on this one, sorry. X. So again, we're trying to find the infinite series, which is what this is. This is an infinite series. And no plus c because we did use a definite integral. Right. So we did use a definite integral there. And my answer is this series. But we're not asking for it in a summation form. Okay, example 4. We can do it 2 different ways, whatever way works for you, but we are given an initial term for this one. So we have f prime of x equals 1 divided by 1 minus x squared, and for that we want to find the first 4 terms of the Taylor polynomial. Really, this is technically a Taylor polynomial, but we know better. It's Maclaurin because it revolves around 0. Okay, so I'm going to do option 1, f prime of x. And if I recognize that it looks like the 1 over 1 minus x, which is x to the n summation, but instead of the x, we're going to put in an x squared. So x squared to the n. Move this up here so it's out of my way. And then we want to find the integral of it. With respect to x. And just like last time, we're going to treat the x as the function and then the n's as just a normal constant. And we're going to do a plus c, but we are given our initial condition of when we plug in f of 0, that would equal 0. We really don't need to do too much work for this one, but if you wanted to pull it out a little bit and try to find what that c value is, pretty easy, right? If you put f of 0, oops, if we know that equals 0, then all of these are going to go to 0, so our c is going to equal 0. So our answer for this is going to be approximate or approximating. Actually, you can use both, but I'm going to use the approximation. First 4 terms, so x cubed and that's option 1. Option 2, we are going to do the exact same thing. I'm going to just copy what I have up there, x to the 2n. I'm going to start by listing them all out. And then integrate it. And we already know from here that c equals 0. And again, same thing, you could just find it pretty easily, but we just wanted the first 4 terms. And there is my answer. Okay, example 5, same exact thing as the last one. So stop and do this one yourself. And then I will do it here after you pause. Looks very similar to the one we just did. So, but this one is a differentiation. So this one's actually not as bad just because you do just need to take the derivative instead of the integral. So try to figure out yourself and then do it with me. Okay, so you should have tried to attempt it. If you didn't, that's okay. But so all we're gonna do is we are going to take the derivative of it. And that's gonna be really nice for us because we already use the same kind of terminology here with using the 1 over 1 minus x, and that'll be x cubed to the n. And this is a nice, easy derivative. We take the derivative, f prime of x. And there we go. Some books do have, the first term would be 0, obviously, just because when you plug in 0 right here, it would be 0. So some books may require you to list the non-zero terms like we have been in the past. What you would just do is just add the term 1. You would change it to a 1 to keep without first term 0 eliminated. And that would be same thing. Either one of these are correct. Okay, and then we're going to differentiate term by term. Take the derivative of what I just gave you up here. And we are going to take the derivative of the term by term x cubed. And we're going to put that back into a series because it does ask us here to find a Maclaurin series for it. So I see a 3, 6, 9. That means I'm going to have to be multiplying something by 3. And you might be like, wait a second, that is not exactly what we did for the last one. So just look at it real quick and kind of see what I did with this. Again, there's different ways to write the exact same thing. So we have 3n plus 3, x to the 3n plus 2. And slightly different, right? You might say, okay, well, we have a plus 3 here and a -1 up here, and it looks a little bit different, but we can manipulate it just a little bit. And it's not that big of a deal. Just look at it like this. So instead of the n, now it's n plus 1, and that would be because we would need to get rid of the first term. So these are the exact same. Oops, goodness. Because of that elimination of the first term. So these are the same. These are all the same. Just a few different ways to write it. So if you put any of these, they would all be correct. All of these are correct. So a bunch of different ways to write the exact same thing. So if you couldn't understand it, just find one, try to manipulate it to get to match one of these. And pay attention to the first term being eliminated. That's the key. Okay, Lagrange error bound. We did talk about alternating series error bound. I did include the screenshot from those last notes, but the Lagrange error bound, or Taylor's remainder as our book calls it, is just calculating the error. Usually it's just the next term. If it says given the second term, try use the third term to find the error. Here is our little formula. Please write that down. And it's kind of like a boundary. This is a very small part of our test, and I'll say this on the next slide too. If you don't understand this, I would try a little bit just to try to get a point, but there's other points on your AP exam that I would try for you guys to get much faster than this. But f of x, infinite amount of terms, minus the nth degree Taylor polynomial, and then you get what's left over. So just like I said for this one, first neglected term, z needs to be chosen carefully. This right here is our z. It looks very much like our Taylor formula. We want to pick our z to maximize. And what that means is usually we're going to try to find the greatest value of whatever it is. Hopefully it's sine or cosine, which we know the greatest value of that is 1, which we'll see here. You will need a calculator for these, but this is a very minor topic. So if this is not working for your brain, it's a little confusing for me as well, but just do a lot of problems if you want to. But again, this is a very minor topic. You might see 1 total on the entire exam, maybe a multiple choice, maybe on the FRQ. Usually it's only worth like 1 point. And again, we're just trying to get as many points. So this would be the thing you would do last. But let's look at example 6. So I'm just going to walk us through it so I don't have to rewrite it and you have to wait for me to rewrite it. All right, so we have use the third degree Maclaurin polynomial for sine of x to approximate sine of 0.1. Then calculate the maximal possible error of this approximation. So the first thing I did was, this is the Maclaurin series for sine. We are given a third degree Maclaurin polynomial. So we have third degree here, right? Because third degree, these match, not the third term, third degree. And then our remainder right here is the next term. And I used a calculator to find that. So we found this with respect to 0.1 of our sine with our third degree. And I used a calculator for that. The next thing we're going to do is we're going to find the fourth degree or the next term. And then I put those here. This is the fourth derivative of that, which is our next term. And I'm going to scroll it here just a smidge down. So my error is the third term, but it's the fourth degree, right? Third term, fourth degree. Two different things. Think of it kind of like n equals 0 is your first term. N equals 1 is your second term. Is your third term. Not for this one specifically right now, but just try to keep that mindset that the n value, sorry, I did make a mistake. Look at that. The n value does not always correlate to the type of term it is. So that's why this is our third term, but then it goes to our fourth degree because it went for the first and then third, and then our next is our fourth degree. So I plugged in that. I still don't know what the z value is. And then I wanted to find 0.1, and this is still our fourth. So we looked at sine. The maximum value of sine is 1. So this kind of goes away. What we're trying to do is estimate the maximum. So our maximum sine is 1. And this is saying if we didn't have a calculator, which is strange, I know, but we're just saying for the sake of it. Our maximum, our error would be this. There you go. You're done. You would not have to simplify this any further if this was a non-calculator section. Usually on the FRQ, it would be no calculator. So this would be your correct answer. If it was a calculator active question like this one is, what you would do is you are going to add this number and this number to get our maximum value. So this is right here, your maximum error, right? That's the highest it can go. That's just your next term. So the best thing for you to do, I know it's like pretty crazy. This really isn't that important. It's just the bound is to know the next term is your error, the absolute value of your error. So we want to find if we have a third degree, we need to determine which term is next for this one. We just counted 1 term, 2 terms. It would be our third term. So that's why it's our third. Okay, example 7. So again, calculator active. The function f has derivatives of all orders for all real numbers. We are given the fourth derivative here. If the third degree Taylor polynomial is x equals 0, woohoo, look at that. We have an awesome piece of information knowing that it's revolving around 0, which means it is a Maclaurin series. This is just the Taylor polynomial function from the front of the error or your next term. And then I'm just going to plug in the information I already know. And you could keep it 4 factorial or 24. Doesn't really matter. So what we're trying to do is we were given the third degree. So we have now our fourth term. Let me say fourth term. Because we know the next term is our maximum error, sorry. Interval 0, 1. We need to maximize. So we need to find the maximum, right? Because we're trying to find the maximum error for this. With this, we have sine It's from 1 to 0. Obviously, we know that sine of 1 is going to be greater than sine of 0, which whatever it is doesn't really matter because the greatest term we want is going to be this. This is our maximum. Right? Biggest, biggest, biggest. And then this would be a calculator question. We're plugging in z equals 1. We are given 0 to 1. We want to maximize that. So these are two different areas of where I got the 1. The 1 from here is from maximizing, and the one from here is from our interval right there. And then we have a calculator, which will give us 0.097. And our last one here, we have let p of x be a 5th degree Taylor polynomial. Let's see, about x equals 0, which means it's Maclaurin anyway. So that's nice. Information is given. Blah, blah, blah. So we are the 5th degree, which means we're gonna find the next term, x minus 0. So just looking at the next term for that one, we are given a equals 0, x equals 1.2. So these are two different things, right? Revolving around it. That's why it's 0. So it's technically a Maclaurin series, but okay, so we're given f of maximum here. They've already given it to us, which is 58.8. I'm just going to plug in things. My x value is 1.2 because that's what we are estimating over the interval, over 6 factorial. And we plug into a calculator. And there you go.